How are we all doing? Happy November. We've arrived in November. That's kind of fantastic. We survived September and October. It's all downhill from here. Downhill's a good thing, meaning easy. We can just coast into the final exam and life will be good. Halloween, how was Halloween? Looks like a few people maybe enjoyed it a little extra and decided not to come, which is fine. Yeah. Anybody bring me candy? No? Did you get candy? I always like candy, but I won't eat candy while I'm lecturing. No thanks. Candy's good. So what you need to do today, you know all the candy's on sale now. Thanks. The day after. Or maybe a couple of days after is best. I'm trying to determine because, the quantity of availability starts to fall, but the sale continues to increase in the coming days. So there's some perfect day to go buy the candy where there's still a nice selection, but there's the most discount. And I don't know what day that is, but I think we need to do some experimentation. Maybe if all of us over the next few days visit a store, make a note of how many days it's been since Halloween and what the current percentage discount is. We could all plot a graph and try to figure out exactly what the optimum day is. And then when Christmas rolls around, the day or two after Christmas, we can all go get the best discounts on candy then too. Let's treat this like scientists. Yeah, I think we should. I told the morning class, they didn't seem terribly interested, but it was 8 o'clock. And most of them were not there because I think they'd all been out last night doing who knows what. And who really cares? Are you okay? Am I the only one who's alive this morning? Too much candy? Did you really have candy? Mm-hmm. Shall we start? You're like, just sit there and ramble. I can put you to sleep by rambling about nothing for a while. I'll put you to sleep by talking about physics too, so that's fine. Might as well at least talk about physics if I'm going to put you to sleep. So let's see, chapter 8. We started just a little bit talking about this idea of conservative forces. Remember, conservative forces, well, they conserve energy. They don't waste the energy. They keep it somehow so that you can get it back. I think that looking at this screen, the first definition of conservative forces and the last is probably the most helpful and the most important. So really quickly there in the middle, at the end of last class, we said that as long as you start and end at the same place, a conservative force doesn't do any total or net work. Another way to think about that is, since we're dealing with displacement, remember, work done is force times displacement. If I end up in the same place, there's no displacement. So of course there's no work, just looking at the equation, okay? As long as the displacement is 0, there's going to be no work done. But the last one is perhaps the most interesting. The work done by a conservative force is independent of the path, meaning it doesn't matter how you get from the starting point to the ending point. It's going to be the exact same amount of work. So let's say, for example, I decide to lift a box, and I lift it a certain displacement up like this, which means that we started here and went to that final location, so the displacement, delta y, is given by that line. The entire time I'm lifting it, well, the force of gravity is pointing downward. So Fg is like this. So from our work equation, well, those are in the opposite direction, which means gravity is doing negative work, and the force times the displacement tells me how much work is being done by gravity. So if I ignore the force that I'm exerting, we're not worried about the work that it's doing. I'm worried about how much work is being specifically done by the gravitational force. It's going to be negative Fg times delta y, where delta y is the displacement from where we started to where we ended. Okay? We should know how to do that at this point. But what if instead of just lifting the box directly up, we got a little more creative with it and decided to start here and go, wee, there we go. The displacement is still the same amount, okay? I don't know why anybody would lift a box like this, because that just doesn't seem to be terribly efficient, okay? The gravitational force the entire time still points directly down. So really, from the equation standpoint, nothing has changed. The work done by gravity is still minus Fg delta y, and all those values are identical. The amount that you would calculate for the work done by gravity doesn't change based on how you get from point A to B. It just matters what those points are. You remember back in chapter 2, we talked about distance and displacement? Yes, maybe. Anybody? Yes, okay. That's really what's coming into play here. Delta y is a displacement, not a distance. Conservative forces worry about the displacement, not the distance, okay? If this bothers you a little bit, thinking like, yeah, but isn't gravity like causing problems this entire time as I go around this weird curved path? Keep in mind that anytime the direction I'm moving is perpendicular to the gravity, it's not doing any work. So there's a lot of points in here where I'm sort of moving sideways instead of up. During those moments, gravity's doing no work. It's only when I directly try to go against gravity that gravity's doing work. So you might look through this little picture and say like, oh, gravity's doing some work here, and gravity kind of has a component of work there, and it's doing work there, and it's only the little segments of it where I'm going against gravity that are contributing. The perpendicular motion doesn't count, okay? So, 3 things. First of all, conservative forces don't lose work, don't lose the energy. Second of all, they do no work if I start and end at the same place because there's no displacement. And third, it doesn't matter how you get from point A to point B, it just matters how far you ended up away from where you started, okay? All of those things, if any one of them is true, then really the other 2 are true, even if maybe you can't see it right away, and they apply only to conservative forces, all right? Now, if it helps, let's switch over to non-conservative forces, and we're going to contrast all 3 of those. And maybe you can start to better understand conservative forces just by seeing how things behave when a force isn't conservative. So you can see the definition up there is kind of, well, vague. It's just the opposite. Anything that doesn't meet what you saw on the previous slide is described as non-conservative. So for starters, we have non-conservative forces. They don't conserve energy. Instead, they lose energy. They don't keep it around. You can't get it back. They just lose it, which is kind of sad, all right? Notice that lost is in quotes, meaning lost-ish. Here's a way to think about it. That energy really never goes away. It can be converted into other forms, and those new forms of energy might be really, really difficult to try to get the energy back out of, all right? So for all practical purposes, we might say that it's gone because I can't retrieve it, but it's really still out there somewhere. It's just hard to get back. So for instance, this morning started, I filled myself with energy in the form of coffee and Pop-Tarts, as one does, right? All self-respecting adults, coffee and Pop-Tarts. Yeah, I'm not really an adult, but whatever, it's easy, it's tasty, I like it. My wife hates that I eat the Pop-Tarts. She's like, you're gonna kill yourself eating Pop-Tarts. And I'm like, I know, but like they're right there, they're in the little package. I can just grab one, hop in the car, drive and eat. Otherwise, it's like, what am I gonna do? Like fix things and sit down at a table or something? Like, what is that? Like, I don't understand how this works. So I supplied myself with fuel, and then I come here, right? And I do work, all right? I walk around, I vibrate vocal cords, which moves air molecules, which eventually run into your eardrums and vibrates your eardrums, right? See, I'm doing more than you think I am. Like, it takes a lot of thought to vibrate vocal cords, and vibrate air molecules, and vibrate eardrums, all right? Also, some of that goes into like like running into the floor a little bit, and some of those air molecules that I move like run into the wall. Like that energy that came from the Pop-Tarts gets pushed out into the room as I do a lecture, all right? And at the end, it's like, oh, time for another Pop-Tart, right? More energy is required. The reason why more Pop-Tarts are required, or at least in the case of this class, maybe it's lunchtime, is because the energy is now sort of lost. I can't get it back. Like, I put it out into the room, you stole it, thank you, and you don't give me my energy back when you leave. Like, what we should do is I should stand at the door when everything is done, and I should be like, okay, give it back. And like all of you should give me a piece of candy as you leave, right? And that's your way of giving energy back. Or maybe what you don't see is like after everyone leaves and you're all out of here, I like turn the lights out. I look around a little bit and sneak back into the room, and that's when the magic happens. Because I have a technique for recovering my energy, and I come back and I like close my eyes and I go, and I get all the energy right back out of the room, and then I walk out like, yay, don't need lunch. Well, first of all, that'd be weird if you like caught me doing that. Maybe you leave and walk back past this way and you're like, why was he doing it there? That's so creepy. I can't do that. There's no way for me to do that. The energy is basically impossible to retrieve. It's not gone. It's still out there somewhere doing something, but it's essentially been converted into forms or dispersed so much that I can't get it back. That's what we mean by non-conservative forces. So all of you out there like listening and maybe catching those sound waves, those vibrations, you're doing non-conservative work through the means of non-conservative forces on all of those vibrations in such a way that you don't store the energy, you just sort of consume it, okay? So if we were to think of a force that we actually know about as opposed to all this weird imaginary stuff that I've been talking about, maybe we could talk about friction. Friction is an example of a non-conservative force. So let's say that maybe there's a box on the floor, and then maybe I kick the box to give it some velocity. Okay? So I kick the box, boom, kick the box. There it goes. You can imagine it's going to slide some distance and stop. And that's going to be the end of it. Yay. Over here, the box stops. So we might say that it has some displacement that looks like this. Let's call it delta x this time. And the entire time it slides, friction is exerting a force on it. In which direction? It's moving this way, so the force is the opposite way, right? So let's just kind of draw that in like this. The force of friction is the opposite direction. Displacement to the right, force of friction to the left. We know that that's negative work, and we also understand that, well, the box is slowing down, so friction must be taking energy away from the box. That is all the definition of negative work. So the work done by friction is minus the force of friction times the displacement. It's taking energy out of the box and really just getting rid of it, okay? Where's it going? Well, you can imagine there's probably a little bit of heat generated between the floor and the box due to friction, but it's going to be really hard to measure, but there's a little bit there, and it's kind of dispersed across the floor. It probably makes some sound. You just hear as it goes across the floor. That's a conversion of energy from the kick into another type. Some of it is probably due to just like maybe slight like deformations in the box, like as it slides, maybe the cardboard or whatever it's made of is bending a little bit and stuff. There's like these little different places that energy is going, doing other forms of work. And by the time it stops, like it's taken all the energy from the kick that I put into it and sort of just thrown it away. It's almost like all those little frictionites. You remember the frictionites? I don't know if we called them frictionites, but that's what they're called, the little creatures with their arms. It's almost like they're like, I'm going to take the energy and throw it away. I don't know why they would sound like that, but you know, so they're like, energy in a box, throw it away, throw it away, throw it away, throw it away, throw it away. And then by the time it's done, they've just like taken all the energy out of the box and just disposed of it. Very wasteful little creatures. Frictionites, I don't know what their deal is. I wonder what they look like. I feel like I should draw them if I was an artist. Maybe some of you have had nightmares about them already. And then you woke up the next morning and you're like, oh, must draw. And you've got like diagrams of frictionites now pasted all over your bedroom. And now that would creep me out, and I hope you never tell me about it. So, no, all right? So the friction takes away the energy and just consumes it, wastes it, converts it to other forms where we can't get it back. Now, if we were to stop right here and think about the motion of the box, up till now, it's not really any different than gravity, right? Think about what happens with gravity. Like if I take an object and just toss it up in the air, well, what happens? It goes slower and slower and slower and slower and slower and stops. What did I do here? I kicked an object. It goes slower and slower and slower and slower and slower and slower and stops. So far, they're exactly the same. It's what happens next that really defines the difference between those two forces and between conservative and non-conservative. In the case of friction, the box just sits there. It's done. No energy. It's very sad. In the case of gravity, what does gravity do next after the object stops? Yeah, it throws it back, right? It takes the object and it says, here you go, and it throws it right back at you. It took the energy out to stop it, and then it says, you can have that energy right back. And by the time the ball comes back to my hand, it's basically going the same speed as it was when I threw it, roughly speaking, as long as we ignore air resistance, okay? It didn't waste the energy. Instead, it stored it temporarily and then put it back in the form of motion once again, okay? Friction doesn't do that, right? Friction's kind of greedy. Like, I'd like to be able to kick the box and be like, come back, box. Doesn't happen. Friction won't play nice. Gravity does. Gravity's like your friend, right? You can throw a ball up and gravity says, here you go. Yay. Thank you, gravity. But friction, you kick the box and then you're like, I'll have to go kick my own box back. You kick it back over. It's like, in one case, you have a friend that will play. In the other case, you just have to play alone. It's very sad, okay? Do you see the way the two forces behave differently? They take the energy, one gives it back, one just wastes it, all right? Does anyone have any questions so far? Kind of get the idea? Maybe you're sort of okay, all right? So let's go to the second case. If a conservative force does zero work, if I start and end at the same point, then a non-conservative force should do non-zero work if I start and end at the same point. So let's think about that. Instead of what we had before, where we just had an object that went up and down, let's say that this time we have a box on the floor. I'm sort of looking down on top of it. And maybe I kick the box this direction. So there's a kick. And then maybe I kick the box over this direction, and then I kick it back to where we started. Okay? So kick the box there, and then kick it over there, and then kick it back to where we started. So we have a closed path, a closed loop. Because it's a non-conservative force, think about how much work it does along each path. Maybe this is delta x, and the friction force is in the opposite direction. And maybe this is another delta x, and the friction force is in an opposite direction. And maybe this is another delta x, and the friction force is in the opposite direction. For all three parts of the path, friction is doing negative work, sapping energy away and stopping the box. And all of them start to add up, right? It's not like there's parts of it where there's zero work and parts of it are negative and part of it positive, and you add them all up and just gives you zero. Instead, it's like we have the work done by friction is equal to negative friction force delta x, and then another friction force delta x, and then another friction force delta x. That's 3 times the friction force delta x with a negative. That negative is not working for me. Let's try that again. Okay. So all of those paths just sort of kept accumulating more and more work done by friction. There's never a case in that path where the friction flips to positive and it cancels out and I get 0 when I get back to where I started. Okay? Notice something that's happening with the friction force. It keeps changing direction, right? It's based on which direction the object is traveling. Gravity is just always pointing down. It really doesn't matter what's happening. Here we kept changing the direction of the object, and gravity is just like down the entire time. Friction changes direction based on the motion. Boy, that'd be weird if gravity did that too. What would that even mean? You know, like depending on which way you're going, gravity points different directions. That would be a weird world to live in, right? Someone should like explore that and write a novel, you know, sci-fi novel. We're on a weird planet, gravity changes directions all the time. Yeah, it's not for me to do. I'm too busy. One of you write it, I'll read it later. Send me a PDF. Sounds good, all right? So number 3, the work for a non-conservative force is dependent on the path. Depending on how we get from point A to point B, we're going to get different values for work. So if I decide to, once again, let's say kick the box, and let's kick it from here to here. Friction does a certain amount of work equal to the friction force times the displacement, and it's negative. But if I decide to get there a different way, and maybe I say, ooh, let's go over here. Whoa. And then let's go here. Let's go there. Let's go here. Let's go there. And then let's go to the same place. Well, all of this friction is going to add up. It's doing negative work the entire time. And even though I ended up at the same place, the blue path and the red path aren't the same amount of work. Okay? We kind of saw that just based on what happened above. This is going to be more work, not the same. You remember we talked about distance versus displacement? Friction and non-conservative forces, they care about all this distance. Conservative forces don't. All they care about is displacement. Okay? So really the difference between conservative and non-conservative forces sort of comes down to 2 things. Conservative forces just have like this consistent direction. Okay? In the case of gravity. And they also are only concerned with displacement. Non-conservative forces have a case where we have this changing direction, and they're more worried about distance instead of displacement. Okay? Who's got questions before we start to use some of this a little bit? Anybody? Anything that makes some sense? Yes?
Can you write that down on a slide soon, what you just said?
What I just said? I'm going to write it down on a slide right now. Let's say conservative is about displacement. Non-conservative is about distance. Let's put up here also cares about. And also the conservative force has a consistent direction, and non-conservative changing direction. There we go. Good. Go on. So let's move forward a little bit and finally start to use a little bit of this. And we're sort of building to something. It's kind of like chapter 7 and 8 has a whole lot of like a little bit of this and a little bit of that, and a little bit of this, and it's like little parts of this big thing we're trying to construct. Here in about 15 minutes, I'm going to show you what we've been building toward. You have to understand all these little things for this big idea to make some sense, okay? So now that we know what conservative forces are, it is only conservative forces that have potential energy. Only conservative forces have potential energy. And if you think back to the definition of conservative, it's only conservative forces that store energy. Non-conservative forces just throw it away. So they don't have a way to store the energy. You can think of conservative forces, I think I said before, as almost like they have a backpack. And it's like when they do stuff, they take the energy out, they put it in the backpack, and then later on they can retrieve it. Non-conservative forces don't wear a backpack. I don't know if that makes any sense at all, but maybe it helps you kind of remember what's going on, all right? So potential energy is a storage system for energy, and it's a storage system and a backpack that only conservative forces have. So different conservative forces are going to have a different equation and a different type of potential energy that we're going to learn about in just a little bit. The 2 things I want you to remember about this is that when thinking about potential energy, think about position. Every equation we have for different types of potential energy will have position in them. It's about where the object is located. Okay? And also, potential energy, again, is like energy that's just waiting to happen. It's energy that's waiting to be let loose, and it'll be let loose in the form of motion, in the form of kinetic energy. It's just like bottled up kinetic energy that's waiting to get out. Okay? So, a few key points to this. First of all, our unit is consistent with everything we've had so far. It is the joule, which is the same unit for all types of energy and for all types of work. The unit is the joule. Potential energy is a scalar. You don't have to worry about direction when it comes to potential energy. There was something else I was about to say, and I lost it. Somebody remind me what it was. That would be impressive if you did. You were about to say blah. That would creep me out. I would have to leave there too. What was it? Unit was a joule. It's a scalar. I know. You're going to see two different symbols for potential energy. I like to just write it as PE. Hey, potential energy, right? It's like straightforward. There's no guessing. If you look in the textbook and maybe even in the homework, sometimes you'll see U as representing potential energy. And I think that's a little more maybe confusing. It's a little bit more abstract. It's the same thing. Two different symbols for the same thing. I'll try to be consistent with using PE, but don't let the U confuse you. Confusion. And then finally, a general equation that relates potential energy back to work. This will apply, when I say general equation, it's like for all types of work, for all types of potential energy, this works. Once again, boy, I can't stop using words that I'm using up here to describe things. When you get to Physics 230, which all of you will, it's going to be fantastic. You're going to love it. It's going to be great. You're going to learn about all sorts of other new things. This equation I'm about to give you will still apply even when you're still learning about new forms of potential energy next semester. Okay? So this works for all cases, not just things we're about to talk about. And it's a really simple equation because the only thing it has is a negative sign. It says that the change in potential energy is equal to negative the work. And specifically, let's make a little note that this is the work done by conservative forces, WC. The change in potential energy is equal to negative the work done by conservative forces. So these always have opposite sign. Let me see if I can explain. We'll go up here. For example, let's take a ball and let's throw it up. All of a sudden that turned a little disgusting. We have a ball that's thrown up. No, not at all. We're going to take a ball and we're going to throw it straight up in the air. Okay? Let's think about what happens with the work done by gravity and the stored energy of the ball as the ball goes higher and higher. Okay? So here's a ball. It has some velocity. And as it goes up, it goes slower until it gets to the top, and you might imagine here it stops. Okay? The ball has velocity, it's going to go slower and slower, and eventually it's going to stop. The entire time it's displacing in this direction, the gravitational force is the opposite direction. Okay? So is that positive or negative work? Negative work, right? So we're going to have negative work being done by gravity, which should correspond to a positive change in potential energy. Okay, let's think about that. So a positive change in potential energy is the same thing as saying it's increasing. Well, as it goes up, think about the backpack. Got the backpack, right? As the object goes higher and higher and higher and slows down, this negative work that's being done means that gravity is taking energy out of the ball. And where's it putting it? In the backpack for later use, okay? Well, if you think about what's happening to the backpack, the amount that's being stored in there is growing, right? It's doing work, taking energy out of the ball, and storing it. So negative work corresponds to an increase in stored energy, okay? One is negative, one has to be positive. Let's make sure that that also works as the ball goes down. We'll say as the ball falls. So it goes up, reaches the stopping point, and here it is stopped, or we'll say at rest, and then it will fall. And as it goes down, it has a growing velocity. So we'll say it's speeding up. Now the displacement is in that direction. The force of gravity is in the same direction. What type of work is it doing? Positive work, right? So now I have positive work being done by gravity, which should correspond to a negative change in potential energy, which means decreasing. Positive work being done. Positive work means put energy into the object, right? As this is going faster and faster, you can imagine the force of gravity is now taking energy out of the backpack and putting it into the ball, making it go faster and faster. So the amount that's being stored is dropping because it's using it now on the ball. So positive work means the amount that I have stored is decreasing. Do you see how those two things are inverse? Always, always. One is positive, the other has to be negative, and vice versa. Okay? Are we still doing okay? I'm looking at you. I can't tell. I have no idea. You all have great poker faces. Maybe you should apply those somewhere because they're really working. Like, it's hard to tell. Do you understand? Do you understand? I think what I want is to we should develop a system that if you don't understand, you just get to the point where it's like, oh, I can't take it anymore, you should just stand up and run into this wall. And that'll give me just a clear sign that oh, I got 4 people stacked up on the wall. Things aren't going so well. Plus you get your frustration out, right? You're just like, I'm frustrated with not knowing what's happening. Yeah. And then I don't run into it too fast. Just, that'll give me an indicator over here, counting people. You had a question?
I think this is a great example, but how can we do the math sides of this example? If
the math for this?
Yeah. Or how would you write that on
You need this slide. You need the next slide for that. We need a little bit of math that goes with that last example. So as far as how much is being stored, how much energy is there, we've got a couple of equations for that. We're going to start with gravity, since that's what we were just talking about. Gravitational potential energy will tell us how much has been stored in the backpack, again, based on where the object is. Okay, so we're going to represent gravitational potential energy like this, PE sub G. And it's equal to the mass of the object times G times its position. Remember, I said potential energy is going to be about position. So it's about where it's located. So if you think about this previous example, as the object is at different locations, I'm able to calculate how much potential energy it has, okay? The key here is that you get to choose, once again, where y is equal to 0, as well as the positive y direction. So just like we did all the way back at the start of chapter 2, you need to pick those two things, okay? Which might bother you a little bit, because if we all pick a different y equals 0, we're all going to calculate a different value for the potential energy. And we're all going to be correct. Yay. Isn't that fantastic? All of a sudden, it's almost like any answer could be correct. Yes, it could be. Okay? If that is disturbing you, let's think about it this way. If the potential energy is changing, okay, so maybe we're like, ooh, my ball has a potential energy when it's at this location, and it has a different amount when it's at this location. How far it is above the ground has changed. Now, if one of you decides that y equals 0 is here, and another person decides that y equals 0 is here, but then you calculate that change, it's not going to matter what number you calculate for here and what number you calculate for there. When you subtract the two, everyone's going to get the same value for how much it's changed. Okay? Yes? Would you agree with that? Okay? So if this is y equals 1 meter for one person, and this is y equals 2 meters for that person, and for the other person, this one's 2 and this one's 3, right? They're 1 meter apart for both individuals, okay? So that if I calculate how much the potential energy has changed, the difference is still going to be m times g times 1 meter, all right? What's going to matter when we move forward a couple of slides is always, every single time, we're actually going to be calculating how much the potential energy has changed. So that where you choose y equals 0 to be, it's sort of just going to be a wash for everybody. It's not going to matter, all right? So let's see, what should I add to this? This g here, remember that this only applies near the Earth's surface. If you're going to use 9.8, the only way this works is near the Earth's surface. If you get too far away, 9.8 doesn't, is it 9.8 anymore? You have to use a different value. So if you're going to use the g constant that we use, this only will apply near the Earth's surface, right? Let me just see what's on the next slide. Hold on a second. Oh, how far are we away from the thing with the thing that I wanted to do? Okay, good. We're in a good place. So one other type of potential energy that we'll learn now, I can't remember if there's more in this semester, but there'll definitely be at least one more next semester. And that is the energy that's stored by a spring, which we will represent as PESP, which also implies that spring must be a conservative force. It is the second one we know about. Gravity and spring are both conservative forces. And the potential energy that's stored by a spring is equal to an equation we saw toward the end of last chapter, 1/2 kx squared, which is the same as the amount of work that's done by a spring. Remember that k is the spring constant, and x is how much it's been stretched or compressed. So this is the amount of stretch or compression. So again, it's about a location, okay? It's how far I've moved the mass or the spring away from its equilibrium position. Two equations that we'll have for two different types of potential energy, which correspond to two different conservative forces, okay? So let me ask if it's possible, in any case, for the gravitational potential energy to be a negative value. Is it possible to get a negative value? Who says yes? Who says no? Who says, I have no idea? Who says I refuse to vote? Well, those people aren't going to vote. So that's a little confusing. Okay? Let's see. Is there a floor below us right now? I have no idea. Is there another floor down there? There's not? You sure? I have no idea. I really don't know. I haven't looked to see if there's a stairwell and it goes down. I don't know. There could be a floor over there. It could be a basement. I don't know. Anyway, let's say this. Let's say that this class is up there on the next floor, right? If we were up there doing experiments, doing calculations, we might say, hey, let's let the floor of this classroom be y equals 0, right? That's the floor of that classroom. And we would do all of our measurements based on that. And when an object was a meter off the floor, we would say that's y equals +1 and so forth. But then what about us down here in this room? If that floor of that room is y equals 0, well, then all of us have negative positions, right? Which means it's possible for us to have negative potential energies in our equation because we'd plug in negative values for y. So it's all about where that y equals 0 is located. You may choose a place that's convenient for you, but other locations relative to that could have negative positions, and that's totally okay, all right? So yes, you can have negative potential energies because you can have negative positions, all right? If we were to stretch a spring 2 centimeters instead of 1 centimeter, how would the work compare in those two cases? And remember, the work for the spring is the same as the potential energy for the spring, which is 1/2 kx squared. So what we're changing is x. Anybody want to shout out an answer that you think is correct? 4? I like 4. All right, if all of a sudden x is twice as much, so 2x, 2xx, all right? X is twice as much, and then we're going to square that. So all of a sudden I've got a 4 that's there. It means it's going to take 4 times the amount of work to stretch or compress it twice as much as before, okay? How about this? I'll let you read it while I draw a diagram. It's just we hear the tables in here multiplying. There for a little while we had one little table, and then it switched out to a different table. And then the different table grew 2 other tables that we have never seen before. So I don't know what's going on here. I wonder where the original table went. We definitely don't have conservation of tables. That's not happening. What do you think? 1, 2, 3, 4, 5. As the mass goes down, what's happening with the spring? It's getting stretched, which means more energy is being stored in the spring. So PE spring is increasing. What's happening with the location of the mass with respect to y equals 0? As it goes down, we could say that the gravitational potential energy is dropping because y is dropping, right? So that means number 2 is the right answer. As the mass goes down, more energy is being stored in the spring, but less energy is being stored by gravity. Okay? Let's move over to this. And this is what I've been wanting to get to. This is one of my favorite topics of the entire semester. So get excited. You're like, uh-oh, that should worry us, maybe. If it's his favorite, we're going to hate it. No, you're going to like this. This is going to be fantastic. We're going to do a problem here in a minute, and you're going to be like, ooh, that problem confused me a lot when we did that problem before, a different way. And the way we're going to do it is going to be very, very straightforward and much, much faster than what we did before, okay? That is the relationship of everything that we talked about in the last chapter and in this chapter. We talked about kinetic energy previously, and now we're starting to learn about potential energy. All of these things are connected to each other because kinetic energy plus potential energy has a name. It's called mechanical energy. The sum of kinetic energy and potential energy is called mechanical energy. With this equation, we can say that this value, mechanical energy, is a constant if one thing is true. If only conservative forces are acting. As long as there's not a non-conservative force that's involved, then the amount of kinetic energy the amount of mechanical energy something has stays the exact same value. And it's made up of some combination of kinetic and potential energy. So the amount of each of those that you have, how much kinetic and how much potential, they can change. They can go up and down, but the sum
has to stay the same. This staying constant is what we call conservation. It's not changing, it's being conserved. So I can write a more extended equation and say that the sum at some initial point in the problem has to be the same as the sum at some later point in the problem. So the initial kinetic and potential energy has to equal the final kinetic and potential energy. And it turns out that this equation is going to come back to haunt you many times, including next semester, and maybe for the rest of your lives after you change your major. At which point it's not really a haunting anymore. It's more like you're haunting that equation, right? You kind of flip it around. So chase the equation, don't let it chase you. It's deceptively simple and powerful in that we have equations for everything that's in there. Every single term has an equation of its own, and potentially multiple equations. At this point, we only know of one type of kinetic energy. It's 1/2 mv squared. We'll learn of more types later on. But for potential energy, we know of two types. So this could be mgy, or 1/2 kx squared. Or as we saw it in that multiple choice question, it could be both in the same problem. So you can start to imagine that this equation that you start with can like rapidly expand into a bunch of stuff. And as we learn about more types of kinetic and potential energy, it can get like bigger and bigger, but it's always the same starting point. It always starts with the boxed equation. So let me explain to you a little bit about how this equation works. And to do that, we are going to go back once again to, we'll say, a ball thrown up. Blech. Okay, same exact thing, just to give you a feel for what's happening. So let's say that for starters, the ball is given a velocity. Let's call that velocity initial. It's going to go up, go slower and slower, and stop. And then, of course, it'll turn around and start going faster and faster and end up with essentially the same velocity going in the opposite direction. I think we all understand how tossing a ball into the air works, right? Because gravity is fun. Gravity likes to play. Gravity is friendly. Gravity is your friend and wants to play ball with you. Now it makes that gravity sound like a ghost or something. I don't know. Now you're going to go around and be like, I have an imaginary friend. His name is Gravity. Yeah, that'd be a cool kid. I'd like to meet that kid. Scared kid. So let's talk about what's happening with the energy. And we're going to do this by drawing something that I'm going to call an energy bucket. An energy bucket. And the energy bucket is comprised of two parts. It has a kinetic energy and a potential energy part, and it has really high walls. So if I put some energy into this bucket, like, and I move the bucket around, none of the energy ever gets out, but it can like change sort of which chamber it's in. It can sort of slosh around and go into the different parts, but the amount I put in here stays constant. It doesn't change. There's no hole in the bucket, and the walls are too high for any to like splash out, okay? So let's say that I start by throwing the ball upwards, right? I have to do work on the ball to give it velocity, to give it energy, to give it kinetic energy. So I do work on the ball. You could think of that as the process of me like pouring some energy into my bucket, okay? And when it starts out, maybe it has kinetic energy like equal to say this amount, right? So that corresponds to this initial case where I threw the ball. It has kinetic energy, and maybe if we added to that this is starting at y equals 0, it has no potential energy when it starts. So I do work to put kinetic energy into the ball, and that's all it has when it starts, okay? Now think about what happens with the energy as the ball goes higher and higher, right? Gravity is going to do work on the ball to slow it down, meaning it's going to start taking energy out and putting it into the potential energy backpack, all right? So you could think of the trip as the ball goes up as this kinetic energy sort of getting moved over here, and that's being done by negative work from gravity. So as it goes higher and higher, just think about the levels of what's happening. Like, I can't get any more energy. If any goes over here, it has to correspond to a decrease in kinetic energy. So it's like kinetic energy goes down and potential energy begins to fill up. Okay? That process is happening as the ball goes higher and higher. Remember, it's going slower. That means less kinetic energy. And it's also getting farther above y equals 0, which means more potential energy. When it gets to the top, think about what that looks like. When it's at the top, let's draw another one of these. All of it has moved over. We have the exact same amount. It's just now over on the potential energy side. Okay? It's not moving. No kinetic energy. It's all now stored, waiting to come back out. Okay? And we know that it does, right? As it comes back down, well, this is going to move back over here because of positive work being done by gravity. And then the levels are going to change again. As it falls in height, this level falls and the kinetic energy begins to fill back up. Okay, so that when I get to the bottom, we could say that it looks like this one. Again, the one on the left. So it transitions between these two states. This is at the bottom, it moves into this case at the top, and then it goes back to being like that. Kinetic energy is being traded with potential energy, but none ever goes away. Does that help you somewhat understand the interchange of sort of how these types of energy are playing with each other? Yeah? Okay? I think we have to do an example. We're going to work 2 examples, and then we'll be done for the week. The first one is a little longer. The second one, a little bit shorter. Okay, so 2 examples is what you have to get through at this point. You can do it, even though it's a little warm in here. You're a little sleepy. I'm making you a little sleepier. I'm kind of wondering if I could put you all to sleep. Just turn the lights out. Next thing you know, you're all hypnotized, and I ask you to just stand up and give me candy. And all of you are like, candy's just coming out of everywhere. It's like, yay, have all the candy. And then I'm like, when I snap my fingers, I will disappear, and your candy will be gone, and you'll be happy about it. And then you'll all be very pleased that your candy is gone, and I'll feel great, and you'll feel great, and I'll go have some more Pop-Tarts, and life will be fantastic. So we're going to do a projectile motion problem. Also, we refer to this as 2-dimensional free fall. We've done this problem. You know how to work this problem. At least you should. If you don't, if I present this problem, you're like, I don't know how to do that. You need to go home and figure that out. Ask me questions, work with other people. You should be able to work this problem using the techniques of chapter 4, okay? But I'm going to teach you a new way to do a problem like this. So let's say that we have an object that's sort of on top of a building of some type. The building is 12 meters tall, and we're going to maybe have a ball here that we kick. We'll say that's 60 degrees, and this is 16 meters per second. Okay? We're going to kick a ball off the top of a building at 16 meters per second at an angle of 60 degrees, and we all kind of know what that looks like. It's going to go way up to some height, and then it's going to fall back down to the ground. Okay? So, you should be able to use kinematics and find things like, how high did it travel? How much time was it in the air? How fast was it moving just before it struck the ground? All those things you should be able to find. So maybe like max height, time, V final. Go use this problem as practice, okay? You should get the exact same answers I'm about to get for at least 2 of those. We're going to find 2 of those 3. So what I want to start with is finding this maximum height. So let's say that that is y final all the way up here, and I'm going to call that the final position of the problem, which means initial is over here at the kick. Okay, initial to final. So part 1, find max height, which is y final. Okay. We're going to do that using conservation of mechanical energy. So we're going to write out the equation we had on the previous page, and we're going to plug in all the stuff, and then the problem's going to be done. Wow. It's a powerful equation. Don't wield it without some respect. I don't know. I should teach this whole class from the standpoint of like it's like medieval or something. And all of these are like magical equations. I don't think I've got that in me. That sounds like a lot of work. I don't want to do that much work. Instead, I'm going to write this equation out. But it is powerful, so be careful with it. Kinetic plus potential equals kinetic plus potential for that initial and final position. So I would suggest looking at the equation and starting out by just thinking about if any of the terms are 0. Are there any points where it's not moving, which means the kinetic energy would be 0? Or are there any points where it's at what we've called y equals 0, in which case I could make the potential energy 0. Let's go ahead and say that this ground level all the way down at the bottom is y equals 0, and we should say that up is the positive y direction. So I kick the ball. Is it moving? Certainly hope so. I kicked it. Otherwise, that's sad. What a sad kick that would be. So it has velocity here, so I'm going to write my kinetic energy equation, which is 1/2 mv initial squared. At that point on top of the building, is it away from y equals 0? Does it have some height? Sure seems like it. So let's write down m times g times y initial. Be careful with the next thing I'm going to ask. At the top of its motion, remember it's doing this. Is it moving? All the way to the top. It's going. Is it moving at the top?
No.
Contrast that with this. It's moving, okay? If it was going straight up, right? Straight up, goes up, stops, and turns around and comes back. If it's going sideways, it stops moving up, but it has to keep going sideways the entire time, okay? So it's still moving at that top position. So I'm going to write down 1/2 mv final squared. We'll talk in a minute about how to find that velocity. And then, of course, it's even higher now. So it has a height, and that includes the variable we're looking for, y final. So I'm going to start by just solving this thing algebraically for y final. Do you see anything you can simplify? What was that? Not quite yet, before we do that. Anything you can use to simplify, so that on the next line, we're not going to have to write down as much. Mass. Mass is in every single term, which means we can go yay, 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 yay. All the mass is gone. You may remember in the kinematic equations, there was never a mass. Mass has no impact on something flying through the air like this. It doesn't matter. So of course it needs to cancel out. Now I'm going to solve it for y final, which means just moving one term over and then dividing everything by g. So 1/2 v initial squared plus g y initial minus 1/2 v final squared, and all of that divided by g. And then I'm going to plug in as many numbers as we have, remembering that all of this is just scalars. I don't care about direction. I don't care about sign. It's just how much. So that makes our life a little bit easier. So let's see. This is going to be 1/2 times, what's v initial? 16. It's moving at 60 degrees, but I don't care. It's just how fast is it going. So that's 1/2 16 squared plus 9.8 times 12 minus 1/2 times V final squared, I'll leave that blank for now and just point out how to get it here in a second. And all that's divided by 9.8. Okay. How do I find how fast it's traveling at the top? Any thoughts? What was that? We are going to use some trig functions. I would agree with that. Let's take a look at that launch velocity again. This is 16. This is 60. So I'm just zooming in on that initial kick, which means that this side is 16 sine 60, and this side is 16 cosine 60. There is a key thing about projectiles that you should remember. Remember, it speeds up and slows down, up and down because of gravity. The sideways, there's nothing causing acceleration. If it's in free fall, there's no acceleration in the x direction, meaning that whatever velocity it has in the x direction is always going to be there. It never goes away. So this one, we could say decreases to 0 at the top. This one is constant. So if it's constant, when I get to the top, that component is gone, and I'm just left with this. It's there the whole time. Think about it. All the way there at the top, which direction is the velocity? It's just directly that way. Okay? It's all in the x direction. So 16 cosine 60 is 8. So I can plug that in down below. And now that we have that, you can punch all of those numbers into your calculator, or I can just tell you the answer is 21.8 meters, which thankfully is bigger than 12 because it should be higher now. Hopefully we didn't get a smaller number. So that all seems to make sense. Do you have a question? Anybody? Anything? Yes?
Can you kind of explain that thing with the velocity?
The thing with the velocity. So this triangle represents what's happening over here right at the start. I give it some upwards velocity and some sideways velocity when I kick it. As it goes higher, this vector shrinks. Remember, it's a vertical one-dimensional problem together with a horizontal problem that are kind of happening simultaneously. As it goes higher and higher, you can imagine this arrow is just getting shorter and shorter and shorter until it's 0. And then it flips directions and grows larger and larger and larger. Okay, so at the top, this side is 0, and it's left with just the x component, which never changes because there's nothing speeding it up or slowing it down in the sideways direction. Okay? Anyone else? No? So let's see. Let's do a number 2. Number 2. Let's find the velocity just before hitting the ground. And this half of the problem will go relatively quickly, and then we'll do the other example, which is ridiculously fast, and then we'll be all sorts of done. Okay? So find the velocity just before it hits the ground. So that means, and let's pick a different color for this part of the problem, I need my final position to be all the way over here at ground level. And initial can kind of be wherever I have information. So let's just leave the initial where it was before, okay? If you wanted to move initial all the way up to the top and kind of treat this as like the second half of the problem, that's fine, you'll get the same answers. I'm just gonna leave it where it is at the beginning. So let's use conservation of energy once again. And initial hasn't changed, so what all we plugged in for initial before is still going to be exactly the same. So I can say that whatever we had over here is going to be the same as what we put over there. So that's going to be 1/2 mv initial squared plus mgy initial. just before it strikes the ground, is it moving? Yeah. If it's moving, it has kinetic energy. So we can write that as 1/2 mv final squared. But now, where's it located? It's basically at 0 now, right? We've reached ground level. So this potential energy is now 0, and we don't have to worry about it. So once again, the masses cancel out, and you can move it around and do a little algebra and solve for V final. I'm going to let you do the algebra. I'm going to tell you the V final, which is 22.2 meters per second. You should get those exact same numbers if you do this with kinematics. Please practice that. Final exam is approaching, and you'll need to be able to do that. In fact, it wouldn't be a bad problem to give you a certain problem and say, solve it these 2 ways. Ooh, that'd be kind of fantastic. And then you get to kind of check yourself. You know, like you almost know if you're right if you get the same answer in both directions. Now, before I move to this other example, I want you to think about those energy buckets if you want to. And you can almost like see, it's almost like they're written right there as the equation. See, kinetic and potential, like imagine that's the 2 sides of the energy bucket, okay? So when this problem started, I had a certain level of kinetic and a certain level of potential. I had both of them, some of in both sides of the bucket. As it went higher and higher, how did those levels change? Which one went up and which one went down? Let's just say they start with equal. Does kinetic energy go down or go up as it goes higher? It has to go lower because it's going slower as it gets higher in the air, right? And it's also getting higher off the ground, which means the potential energy is increasing. So we start with some levels, and as it goes over higher and higher, potential energy is growing as kinetic energy is dropping, okay? Then I have some new levels, and what's going to happen is I go to the last part. Notice, when I get to the end, I only have kinetic energy. So it's like whatever combination here I started with, before I get to the end, all of it fills up the kinetic energy side of the bucket. There's no potential energy that's left. No sum change. The amount that's in the bucket never changes. It just sort of changes levels, and when I get to the end, it's like all in the kinetic energy side. Okay? You see it? You visualize it? Your head's not exploding? Okay, let's do one more example, and this is a fast one. I'm going to work it relatively quickly. I just want to give you a spring problem and show you how that works. So we've got a spring. We're going to say it's got a mass. This is x equals 0, which means the spring is compressed. And we're going to say that the spring has been compressed 0.2 meters. Let's see, the K for the spring is 500 Newton meters, and the mass is 2 kilograms. So what's going to happen is we're going to compress the spring like this and then let it go. So the spring is going to push the mass, and then once it gets back to equilibrium, basically the mass is just free to go on its own up the incline somewhere, and eventually the mass will be up here and stop. Okay? We want to find this distance. How far does it go up the incline? So let me point out a couple of different things. First of all, at this location, all the energy is stored in the spring. So we could say this is all potential energy in the spring. When it gets to the end and it stops, what type of potential energy does it have now? It has gravitational potential energy, and that's all it has. When it's in the middle, right here, it's both at ground level and the spring is no longer stretched or compressed. Here it's all kinetic energy, okay? So I start with all spring potential, that gets converted into kinetic, and then that gets converted into gravitational potential, okay? if I just want to find something about where it ends up, I don't really need to do anything in the middle. I can just say all of the spring potential energy, it went through something else in the middle, but it ended up as this other type of energy, which means I can write something that looks like this. I can say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Initial is over here, final is when it stops. Is it moving at the initial position? Is it moving at the final position? It's not moving at either case. So that's 0 and that's 0. And then we get an equation that says what I just described. All this potential energy is equal to all this potential energy. One completely becomes the other. So 1/2 kx squared equals mg y final. All the spring potential energy becomes gravitational potential energy. If you plug those numbers in, you get a y final of 0.51, which is like this distance, 0.51, which almost answers the question, right? I need one other little piece of information. We could say that the sine of 45 is 0.51 over d. So d is 0.51 over sine of 45, which is 0.72 meters of distance like along the incline. Okay? I told you that was fast. Conservation of energy. You can do it, right? We're not quite done yet. There's a good bit left in this chapter, so I'm not going to assign a homework 8 yet. But I hope you've all started homework 7. It's only 5 questions. It's doable. You can finish it before the weekend. That'd be kind of fantastic. Yeah. All right. Have a good Friday. Have a good Monday. Have a good Sunday. Have a good Saturday. That's not in the right order. I'll see you all on Tuesday. Goodbye.